Before starting, I've already created an existing program that includes the necessary block setup configuration. Additionally, I have set up a generic device model on port number 1, which in this case corresponds to a Balluff BNI0085 IO Link SmartLight. I've configured the port with the default settings for this specific type of device, and now I'm ready to proceed with configuring its individual parameters within my program. It is crucial to emphasize that in order to utilize this specific function within the program, we must employ one of the predefined generic devices, which are specified in terms of an output and input byte size. However, it is essential to note that using any of the standard IO Link devices from the default or custom lists will not be compatible with this function. The reason for this incompatibility lies in the specific requirements and byte size definitions associated with each device model. In other words, the device configuration must exactly match one of the predefined generic device models to ensure seamless integration with this particular function. Using a different device from the specified list will likely result in errors or compatibility issues that prevent the function from working as intended. The first step in setting up this project is to import the necessary library, which can be obtained directly from Siemens. Since I'm currently running version 20, but my original version was created in 16, it's essential to perform an upgrade to ensure that all the required functionality is available. Once the library has been successfully imported, the next step is to access the configuration options related to IO Link devices. To do this, I'll navigate to the Types section and then select IO Link as the device type. From there, I need to specify the controller settings, family, base blocks, and finally, the IO Link device itself. I'll drag the selected IO Link device onto my program ladder and create it with a default name. Now that we have our device configured, the next step is to map the data associated with this IO Link device. To do this effectively, I've already created some predefined tags that will be used to reference specific data points within the device. These tags are essential for accurately mapping the data and ensuring that it's correctly interpreted by the program. With my tags in place, we can now proceed with configuring the device settings and defining how the data is mapped and read/written to the device. This process will involve identifying key parameters such as ID, hardware identifier, and other relevant data points that need to be configured for optimal functionality. For the BNI00HL device, we need to enter a specific hex value of B40 for the cap field. This value is a constant that was previously discussed. Let's return to this section. This data block will be used to write to and read from the device when necessary. We'll explore this further in our session later. Next, we need to find the hardware ID number for this port. To do so, we'll go back to our block configuration here. We'll click on the port to select it, then navigate to the Properties and Systems Constraints tab. There, we can find the unique hardware identifier for this port. Notably, each port has a distinct hardware ID number that is specific to the current version of Profinet specification. In our case, the hardware ID number for this port is 282. With this information in hand, we'll create a new data block with an array of bytes set to 232. The system will now be configured correctly. Now that we've completed these steps, let's save and compile our program. We can then download it to the device. To make this configuration more meaningful, I created a watch table with relevant tag data associated with it. This specific tag value corresponds to the brightness setting of the light. In decimal form, this value is 81, while in Siemens notation, it's represented as hexadecimal 51. Now that we have our function block set up, let's run it and verify that there are no errors. Everything checks out, we can proceed to review the array associated with this function block. Upon inspection, we see that the value is indeed 7F7F, which corresponds to the maximum brightness setting for RGB channels. Our next step will be to adjust these values by reducing the overall brightness. To achieve this, we'll set each of the RGB channel values to 10. With our adjustments in place, let's hit OK and proceed back to our function block configuration. As previously configured, we're going to change the read/write flag from false to true. This means that instead of writing directly to these values within our array, we'll now be reading from them and updating the device accordingly. Now that we've made this adjustment, let's review the tag values once again. As expected, the new brightness setting has been successfully applied, as evidenced by the dropped value in the previous brightness setting we had.